So far, we haven't done very much proof in relation to counting. We've derived some formulas, but we haven't proved very many theorems. Counting techniques actually lead us to some of the most beautiful proofs in mathematics, at least in my personal opinion, using a technique that we haven't introduced yet. This technique is called combinatorial proof. The way that combinatorial proof works is we have two things A and B, usually two numbers, and we want to prove that A and B are both equal to each other. So we want to prove something of the form A equals B, or maybe A and B are two numbers specified by very complicated formulas. And the way we're going to do that is by saying that, hey, A and B are both ways of counting the number of possibilities for performing a task. So if I can show that A and B are both formulas for counting the number of ways to perform a task, then I'll know that they must be equal to each other because they are ways of counting the same thing. So let's do an example. Here's a theorem. For any integer n greater than or equal to 0 and any k less than or equal to greater than or equal to 0 and less than or equal to n, it's the case that n choose k is equal to n choose n minus k. Okay, so this is a theorem that says that these two binomial coefficients are equal to each other. Let's do one proof. So we're going to do a proof first that is just pure algebra. So for this pure algebra proof, here's what I'm going to do. I'm going to say, hey, here's n choose k. And by definition, that's equal to n factorial divided by k factorial times n minus k factorial. And I'm just going to rewrite the bottom here a little bit. That's n factorial divided by n minus k factorial. So I just moved this n minus k factorial to be first. And then I'm going to go down here. That's n minus k factorial, because n minus k in parentheses is just equal to k itself. And so that's the definition of n choose n minus k. Okay, so there is really nothing wrong with this proof. It's fine, it's correct, but it doesn't really tell you much intuition. Why is this fact true? What is the theorem actually saying? What does it mean? An ideal mathematical proof tells you not only that something is true, but also why something is true. So let's see if we can learn why this fact is true using a combinatorial proof. We're going to show that both n choose k and n choose n minus k are two different ways of counting the same thing. So, proof. Here's our claim that we will prove. Both n choose k and n choose n minus k count the number of ways to form a committee of size k from a set of n candidates. So this is just a very classical n choose k kind of problem. I want to create a subset of size k from a set of n possibilities. Okay, so let's think about this. Okay, so first of all, let's think about n choose k itself. Well, we know that is actually this number by definition. N choose k is the number of ways to choose the k people from n possibilities. So that's really by definition. On the other hand, let's look at n choose n minus k. And we're going to think about this in a pretty exclusionary kind of way. Instead of choosing k people to be on the committee, so I walk up to k people and I tell them that they're on the committee, what if I walked up to everybody else and told them that they're not on the committee? That would have the same effect, right? If I tell n minus k people that they're not on the committee, the remaining k people must be on the committee. So in either way, I would specify the same set of k people. So in other words, I can consider n choose n minus k to be the number of ways to exclude n minus k people from the committee. So to sum up here, I can form this committee of size k either by specifying everybody who's on the committee, or equivalently by specifying everybody who is not on the committee. Both of these are going to lead me to the same result. These count the number of ways to achieve the same task and must therefore be equal. And that's my proof. By the principle of combinatorial proof, I'm done. I've shown that these two formulas are different ways to count the same object, the number of ways to perform the same task. Since they're both equal to that, they must be equal to each other, and I approve my claim. This particular example is not that exciting because the algebraic proof 1 is noticeably shorter and arguably easier. We could have proven this claim with proof 1 no problem. But as we'll soon see, there are also much more complicated kinds of proofs that we can do, where doing a purely algebraic proof would not be rewarding or necessarily even possible, but doing a combinatorial proof is still easy and intuitive. Let's do an example of a combinatorial proof where the alternative of algebraic proof is quite unappealing. So here's our theorem that we're going to prove now. It's another theorem involving binomial coefficients. So this theorem says that for all n greater than or equal to 0 and k between 0 and n inclusive, it's the case that n choose k is equal to the sum of two other binomial coefficients, n minus 1 choose k minus 1, and n minus 1 choose k. So this is a theorem that you could try to prove with a formula. You could write out all the definitions, you could do a bunch of algebra, you'd have to do some fraction stuff in there, and eventually you would be able to show that these two things are equal. The left-hand side is equal to the right-hand side. But it would be sad, and it wouldn't really tell you why this is true. It definitely wouldn't help you remember it if you ever wanted to remember this. Let's see if we can instead write a proof that helps us see why this theorem is true. What's the insight here that makes this theorem true? So let's write a combinatorial proof. So when we think about our combinatorial proof, it can help us to start by looking a little bit at the structure here of what we're trying to prove. So I notice a plus sign. I'm doing an addition, and that makes me think, hey, I'm doing an addition. Maybe there's going to be a disjoint choice idea somewhere in here. Maybe there's going to be a disjoint choice idea somewhere in here. Furthermore, I have a little bit of a hint because the left-hand side is something that I understand very clearly. N choose k. It's the number of ways to choose a set of size k from a set of n possibilities. So what must be true is that this side, the right-hand side, also counts the number of ways to form a set of size k from a set of n possibilities. It's just doing it in a different way, and apparently in a way that involves disjoint choice. So let's go ahead and write this proof. So my claim is going to be the following. We'll show that the RHS, that's right-hand side, also counts the number of ways to form a committee of size k from a set of n possibilities. We know that's what the left-hand side does, so if we can prove that the right-hand side also does that, then we are done. Okay, so what I'm going to do is I'm going to pick a person, A. Okay, so their name is A, that's just what we're going to refer to them as. And we're not picking them to be on the committee, we're just focusing on them right now. So we're going to pick one person, and we're going to focus on them. And here's the thing about that person, and this is where our idea of disjoint choice is going to come in. Either A is on the committee, or they are not on the committee. You can't be both on the committee and not on the committee. And that means that we're looking at a disjoint choice type of situation. So let's consider how many ways each of these possibilities could occur. If A is on the committee, the remainder of the committee consists of k minus 1 other people chosen from the set of n minus 1 other possibilities. Because if we know that A is on the committee already, there has to be k minus 1 other people to create a total of k. And we know those k minus 1 other people must come from the set of n minus 1 other possibilities, because A themselves was already a possibility and they've been accounted for. So this means that we have to choose k minus 1 people from a set of n minus 1 possibilities. So that means there are a total of n minus 1 choose k minus 1 ways for this to happen. Okay, so that's one case. If A is on the committee, then we're going to have this term, n minus 1 choose k minus 1. On the other hand, if A is not on the committee, then all k members of the committee must have come from the other n minus 1 possibilities. So here, if I know that A is not on the committee, there must be a total of k people who are on the committee, and there are n minus 1 people who aren't A, and the k members must have been chosen from among those n minus 1 people. So this is my other case, and there are a total of n minus 1 choose k ways for this to happen. But now I have this disjoint choice. Either A is on the committee or not on the committee. Those can't both be true, and one of them must be true. So, by the addition principle for disjoint choice, the number of ways to form the committee is, well, we have our two cases. N minus 1 choose K minus 1 for the case that A is on the committee, plus N minus 1 choose K for the case that A is not on the committee, which must be equal to N choose K, because N choose K is also the number of ways to form a committee of size K from a set of N possibilities. So using combinatorial proof, we actually allow ourselves to skip a lot of the algebra. As long as we can interpret the entities involved in our identity, so here's the thing we wanted to prove, as long as we're able to interpret these and figure out, oh, what's this counting, what's that counting, what's that counting, can create a scenario that relates all of these. As long as we can do that, we don't necessarily need to do any algebra at all. We just need to be clever in interpretation and then relating these ideas to each other with combinatorial proof.